I could do the same thing with this rod. I could rub it with this piece of felt and give it a small charge. Now, the felt works okay. I have a piece of silk here that also works. But you know what works the best is cat fur or rabbit fur. But for generations, physics students have walked into physics lectures and witnessed the horror of their professors pulling out a cat pelt and rubbing it on some sort of rod to charge it up and showing them the charging process. I'm not going to do that to you, but I just so happen to have a better version. So I have here the live version of that demo, right? This is Luna. She's not really super excited that I disturbed her nap. But let me do this. What I'm doing, she thinks I'm petting her. I'm actually giving this rod a little bit of charge, right? I'm actually putting charges onto this rod. Of course, those charges have to come from somewhere. Charge is conserved. So they're coming from Luna. Now, let me show you what happens if it works. Conditions have to be right. There we go. Thank you. Back to your chair. So what I did is I put charges on this rod. That is called charging by conduction. Now, charging by conduction can cover a couple different things, but the point of charging by conduction is there is a physical path for the charges to flow onto this rod. So in this case, that was just by friction. What I did then, though, is I took this rod and I touched this metal plate, and you should have seen this lever in here move. And in point of fact, it's still moved. So let me explain how this works. How this is set up is this top metal plate goes through the shell and is connected with the metal armature down here. So this is all one piece of conducting material. What makes a conductor a conductor? Mobile charge carriers, right? So what happens is I put a bunch of positive charges on this rod by rubbing it on the poor cat, and then I brought it close to this plate, and you should have seen something happen. When I touched the plate, you should have seen the lever move. Why did it do that? Well, positive charges, we know, don't like to be near each other. So I had a bunch of positive charges on this thing. In point of fact, I probably had negative charges, but we're going to assume they're positive charges. They don't like each other, but they have no choice to be near each other because I forced them to be here. But when I touch this metal, some of them have the opportunity to jump ship, as it were. And they do so. They jump into this metal. Of course, what happens then is that the metal, which has lots of charges that are able to move around, those positive charges don't like these positive charges, and so they all spread out as far as possible. Imagine being put into a room with 10 other people and none of you like each other. And not even that, you can't even tolerate each other. What are you gonna do? You're gonna move to positions where you are as far away from everyone else as completely possible. That's what these charges in this plate do. I gave this plate an excess of positive charge. That positive charge was immediately distributed throughout the rest of this metal, and they all went as far away as they could from each other. But part of this thing can move. That lever can move, and so the repulsion of those positive charges made the lever move to a position in which it was as far away from its neighbors as was possible. In point of fact, those charges, after a really small increment of time, come into equilibrium. Of course, the positive charges are exerting forces on each other. They're moving in accordance with those forces, but they come really, really quickly to an equilibrium position in which the forces summing up on the charges is exactly zero. Doesn't mean there are no forces. It means the net charge is zero.